Hi everyone, I'm Alicia and presenting with me is also Yunwen. We will be presenting our paper exploring data augmentation in bias mitigation against non-native accented speech. Great. The motivation behind our work is that ASR, automatic speech recognition, should serve every speaker. Currently, it is the norm that only standard speakers can use ASR systems, and everyone who is not standard cannot properly use ASR. This concerns speakers from various ages, regions, and genders. Another important group are the non-native speakers. So until now, bias against non-native accents was quite strong. We tackle non-native accent bias specifically because this has the added challenge of data scarcity. Previous studies have already found ways to successfully mitigate biases against accents through data augmentation, and we want to see how we can further improve the performance. Our research question is thus, how can we mitigate bias against non-native accents in a state-of-the-art Flemish ASR using data augmentation methods? Here we find it important that we do not just reduce the bias between native and non-native speakers, but also make sure that we do not lower the performance for native speakers. Our contributions can therefore be summed up by the following sentence. We systematically investigate the effect of different types of data augmentation for bias reduction against both red and human-machine interaction type, non-native accented Flemish in an end-to-end ASR. To train our model, we use the classic spoken Dutch corpus, abbreviated as CGN, which gives us approximately 420 hours of Dutch speech from the Netherlands and approximately 260 hours of Flemish, so Dutch from Belgium. The speakers in this corpus are native speakers between the ages of 18 and 60 and thus called standard. We also use a Jasmine corpus, which contains native and non-native speech from speakers aged 7 to 60 plus years. This corpus is thus non-standard. We only use the Flemish data and split it into training, validation, and test sets. We end up with 4 test sets: native red speech, non-native red speech, native human-machine interaction, and non-native human-machine interaction. To augment our data, we used 4 different methods, namely the classic spec augment, speed and pitch perturbation, and synthetic data from cross-lingual voice conversion. The voice conversion model was trained with the VCTK corpus, which contains English data, which allows us to create more non-native accented speech. We also combine the techniques. This figure shows the experimental pipeline. So we first compare the baseline models trained on the CGN and either the Jasmine native, Jasmine non-native, or both. We use the best setting, namely the base plus Jasmine Flemish train for the following experiments. The middle part of the pipeline shows the data augmentation methods. We perform speed perturbation, pitch perturbation, and voice conversion, as well as all combinations on both the native and the non-native Flemish data, and add these to our best setting model. We then test our 4 groups: native red, native HMI, non-native red, and non-native HMI on all augmented models.
In this paper, we used the conformal-based joint CTC attention ASR model in ESP-Net Toolkit. we also used BPUNet with vocabulary size 5000. The input feature is 80-dimensional filter bank. We set all the experiments with the maximum training epoch 25. And we also set the number of iterations per epoch the same. We used the average 10 best models with lowest validation losses as our test models. The bias is calculated by the difference between the word arrays on non-native accented speech and native accented speech. We calculated the bias for different types of speech separately, which are HMI type speech and red type speech. Here we show the baseline results. Baseline with spec augment and the data addition results. We can find that the word arrays of the baseline are not that good. That's because there exists the mismatch between the training and test data. The training data is from Zijun corpus and the test size are all from the Jasmine corpus. When we directly combine the baseline with spec augment, we found that the word arrays for all test sets are lower, but at the cost of the biases for both red and HMI type speech. About the three data addition experiments, we found that adding both native and non-native accented speech is the proper choice among the three experiments because it can give the lowest HMI non-native accent bias and give the best word arrays results for HMI NN test size and both native and non-native accented red test size. So we will continuously adding data augmentation data based on this setting. According to the data augmentation results on native accented speech, in this table, we can the blue row means the corresponding augmentation setting on the native accented speech, which can give the lowest bias for the red type speech among all of the 7 experiments. The same meaning for the green row, but the green row corresponding to the lowest bias for HMI type speech. Overall, we can find that adding augmented data from native accented speech can make the word arrays on the native and non-native test size lower, but not well with lowering the bias. We can find for the best bias for red type speech, it only reduced from 4.9 to 4.7, which means the reduction is not that obvious. And for the HMI type speech, the bias did not reduce, it even increased to 0.8. For the non-native accented speech data augmentation results, again, the blue row corresponding to the augmentation setting, but this time on the non-native accented speech for red type speech. For best red type speech, non-native bias. And again, the green row means the corresponding setting on the non-native accented speech, which can give the lowest bias for HMI type speech. We can find that even though after the data addition experiments, the bias for HMI type speech is reduced to 0.2. After we do the data augmentation on the non-native accented speech, it can still be reduced to 0.1. Well, for the red type speech, the best result is 3.2. Compared with 4.9, it reduced by 1.7, and the word arrays on both native and non-native red type speech are reduced as well. So doing data augmentation on non-native accented speech can make the word arrays lower and make the biases lower for both types of speech. Finally, we combining the best results for bias reduction for the red type speech and the best results for the bias reduction for HMI type speech. We found that when we combining both native and non-native data augmentation, it can further reduce the word arrays on both native and non-native accented speech, but cannot reduce the bias further. The same with the HMI type speech. Combining the two data augmentation, the word arrays for HMI type speech can reduce, but the bias increased. However, when we combine the two best citing for red type speech with the spec augment, both the word arrays and the bias can be reduced further, and the 2.9 is the lowest red type speech non-native bias in this paper. For HMI type speech, when combining with spec augment, the bias is reduced back to 0.1. Comparing this result and this result, the bias is the same, but this one gives the lowest word arrays. In summary, from our experiments, we can find that adding both natural data from Jasmine corpus and artificial data generated by different data augmentation methods can reduce word arrays for both native and non-native accented speech and reduces the non-native bias. Artificial native accented speech reduces word array for non-native accented speech, but slightly increases the bias. Doing non-native accented speech data augmentation is beneficial to bias reduction compared with native accented speech data augmentation. And when we do the 3 kinds of data augmentation experiments separately, pitch perturbation performs better than speed perturbation and better than the voice conversion. Overall, adding more speakers or data combined with spec augment reduces the word array for both native and non-native test size and the bias further. In this paper, the bias for HMI type speech is reduced to 0.1, but for the red type speech, the bias still exists. It's about 2.9. Additionally, we only do the bias mitigation experiments for the Flemish language. In the world, there are 7,000 languages, so more research into ASR bias mitigation is necessary. Thank you for your attention, and if you have any questions, please contact this email.